Good morning, everyone. Good morning, everyone. Today, I'm going to present a paper, Gradient Disaggregation, Breaking Privacy in Further Learning by Reconstructing the User Participant Matrix. The authors are Maximilian Lam and extract from Harvard University. And this paper is accepted by ICML 2021. In the following, I'm going to introduce the background about further learning and gradient disaggregation attack at first, and then I will introduce the threat model and attack model of this work. And next, I will talk about the experimental results and end up with a conclusion. So what is federated learning? Generally, in a federated learning setting, there are a set of devices, or let's say the clients, and a central server. And these devices can be our smartphones or smartwatches, which have their own local data set and also has the capability to do machine learning tasks. And the server can be either Google or Facebook server, which will coordinate the federated learning process. The goal of federated learning is to collaboratively learn a shared model across clients without sending raw data to the server. Federated learning is being used by major corporations like Google, Facebook, and Apple to train models on various applications such as next word prediction, sentimental learning, health monitoring, content suggestion, and more. And the privacy is one of the major advantages of federated learning. As I mentioned, in federated learning, the training data will be kept on device without sharing with the server. And in this case, the server has no access to the training data, and hence reduce the privacy leakage of clients' sensitive data. So how does federated learning works? In federated learning, the server will coordinate the clients to update a global model for many rounds until converge. And at each round, the server will at first broadcast the global model to a subset of clients, and then the selected clients will compute gradient or model update on the global model using their local training data. And next, the server will securely aggregate all the model updates from clients via secure aggregation to get the sum of local model updates and use it to update the global model for next iteration. Here, the secure aggregation is one of the secure multi-party computation methods. It enables the server to directly obtain the sum of model updates and nothing else. The reason of using secure aggregation in further learning is that recently studies have shown that the attackers can infer private information from the model parameters like the model update or the model gradient using privacy attack methods like membership inference attack or model inversion attack. By using secure aggregation, the server only obtains the sum of local updates, which prevents the server from getting the individual model updates. Now let's look at what is the gradient disaggregation attack proposed in this work. The gradient disaggregation attack aims to undermine the secure aggregation protocol. It allows the server to recover individual model update of a client using the sum it has and also the client's participation counts or the client's participation frequency, so that the server can perform inference attack on individual model update to violate the user's data privacy. For the threat model considered in this work, it assumes that first of all, the server is malicious and has the ability to fix the global model across rounds. And second, there a fraction of clients will be selected randomly to participate the training at each round. And the third assumption is the server has access to side channel information about the device metrics or device analytics, such as client participant frequency. That is how often users participate across certain rounds. So let's look at the details of gradient disaggregation attack. Here, we let the capital P represent the user participant metrics across n rounds with U users. So P is n by U matrix, and each element represent each element represents whether the user participated a specific round or not. So here, the one represents that user one participated in the round one, and the 0 represent that user two didn't participate the first round. So in this case, each row captures which users participate at that given round, and each column captures for a specific user which round it participated. And let the capital GI, that is the capital individual, represent the individual model update metrics, and each row represent an individual model update at a round. And let the capital G aggregation represent the final aggregated model updates across round. So each row represent the aggregated model update received by the server and a round. So we can see that the aggregated model update is a multiplication of the matrix P and the matrix G. So as we mentioned, the goal of the gradient disaggregation attack is to recover the individual model update, that is the capital G matrix. So in this case, the problem can be formulated as a metric factorization. That is because the server has the aggregation metrics, and as long as the aggregation metrics can be factorized into P and G, it can obtain the individual model update G. To solve this metric factorization, where the left term P is binary, the state-of-art method is to reconstruct the binary matrix P at first. And then with the obtained binary matrix P, G can be recovered. And so to recover the matrix P, we can recover each column of P individually, because in the literature, researchers found that each column of the matrix P, that is PK, is stay on the image of the aggregated matrix, aggregated model update matrix. So in this case, the objective becomes to find PK, that is the participation vector for user key, subject to the kernel of the aggregated matrix times PK. equal to 0, this constraint represents that if this constraint is satisfied, then PK will be stay on the image of the aggregated matrix. So this constraint is to force that PK is stay on the image of the column space, the image of the aggregated matrix. And this the PK is either the element of the PK is either 1 and 0. However, this problem is NP hard. So if the number of rounds and the number of users are very large, it's hard to solve. To solve this problem efficiently, they also leverage the server can leverage the summary information from device analytics to assist in reconstructing the matrix P. Especially as the server will connect the device analytics, periodically it can get the frequency of a specific user's participation. In this case, we can have the total number of participation of user K in a specific time period, which can be represented as CK. So in this case, we assume CK is known by the server, and then we reconstruct a new matrix capital CK and generate such a constraint. Here, let's say the CK represents the total number of user case participation, and the CK is generated in this case. Here, the capital CK consists of J rows, and each row is each row has n elements. So CK is J times J by n matrix, and the small CK is a vector of J element. Here, for example, if we set the total number of rounds as 10, and the window size of for the server to collect the device metrics or analytics as 5, which means the client will collect the frequency of users' participation every 5 rounds. And then the J becomes 2. So so here is a example.
So I have a quick question. So the paper seems to indicate that the federated learning system, the system does need to collect the frequency of user participation. So is that like, do they have any reference or any reason in supporting that? Why do they need the user participation frequency?
Oh, they mentioned that when this kind of like data, the metrics of device during the training is important to management or to the federated learning system or to debug the federated learning. And they mentioned one paper like that is the practical secure aggregation. That paper they mentioned that many of the metrics of our devices will be connected by the server for the maintenance of the federated learning system.
Okay. Yeah, I guess it also is necessary when you want to integrate it with like incentive design things.
Yes.
Zoe, but for those papers you mentioned, this many years ago, right? So I think even for those papers, for example, 2017 CCS paper, it has some limitations, right? For example, the model gradients, it cannot be very huge, so that this kind of scheme that can work. If the model size is very big, probably it cannot work. If I remember correctly, that paper work on some bitwise aggregation, right?
You mean this paper work on bitwise?
No, not this one. I mean the 2017 CCS paper.
But yeah, they have the same issue in this paper, like the dimension of the aggregation cannot be very large.
That's not a kind of a consistence with current trending of of federated learning, right? So now we have a very kind of huge model updates, right? So
yes, but in their experiment, they do like have model that MLP model that is not very small, but is not very large.
Okay, but is that matrix very sparse or is very dense matrix?
You mean the gradient matrix?
Yeah.
It's because it's a linear layer. I think it's hard to say is the specific gradient is sparse or dense, but usually in deep learning, the gradient metric is sparse.
Yeah. Also, I think for that CCS paper, it requires the participation of all members. In other words, it requires the participation of all federated learning clients, right? So
you mean per round?
Yeah, per round. I mean, for that scheme, for that privacy preserving, differential privacy preserving aggregation scheme, for that CCS paper, it cannot be like top K user selection or something, which kind of common in the federated learning setting, right? So, because I mean,
but in this paper, yeah, they assume that a subset of clients participate per round.
But every time you need to set up, the K, say for N user and M user, if I remember correctly, it will be different, right?
Yeah.
You need to generate a certain kind of public K. It requires a lot of time.
Yes, I agree. But I think there are two cases. One case is that the server has the server has to like select the clients, and in this case, the server know who will participate per round. Another case is like the clients will participate depending on its capabilities. So the server, in this case, the server does not know who will participate. It only receive the sum of many local model updates. I think this paper focus more on the second case. In this case, it makes more sense.
Well, nevertheless, it doesn't overcome the drawback of that 2017 CCS paper, right? You still need to consume a lot of time to generate the public K, right? Say, like you said, if every round, different numbers of participation, I cannot I cannot think of how complex the system will be. In particular, I mean, for K generation only and K distribution.
Yeah.
Right.
I think that's a problem of secure aggregation protocol. It's like every round you need to generate the keys.
But that's true. But this paper is based on the assumption of that protocol.
Yeah.
Yeah.
Yeah,
If that
true.
protocol doesn't work well, why we want to, generate this paper, right? So,
Yes.
but anyway, that's kind of too much background knowledge. Okay. Thank you for the clarification.
Okay, let's continue at the capital CK, this matrix. So here is an example. If user I participated in the first 5 rounds for 3 times and the last 5 rounds for 2 times, and then the C11, that is the first vector for user 1 will be the first 5 element will be 1 and the last 5 element will be 0. And the C11 will be 3. So why they set the capital K like this is because when we time the C11 with P1, we restrict it equal to C11. So in this case, and also for C12, the first 5 element will be 0 and the last 5 element will be 1. And when C12 times P1, that is the frequency of users' participation across rounds, will be equivalent to 2. So why they design CK as this is like, if we add this constraint to the optimization problem, it can kind of like reduce the search space of P1. It's like it's limited that in the first 5 rounds there will have 3 elements in P1 will be 1, and in the last 5 rounds, there will be 2 elements in P1 will be 1. So this is a kind of the tricks that they provided to simplify the optimization problem. Sorry, I need to go back to my. So now the optimization problem becomes to find the user participant frequency of each user PK and subject to the matrix factorization problem, the constraint, and subject to the value of the element of PK, and subject to the count of user participant and each during each time period. And this small CK is the information collected by the server. And another problem in solving this problem is that, as we can see that when we mention the aggregated matrix is equivalent to the P times the individual model update. But at that time, we assume that the author assumed that the local model update of clients are the same. But in practice, not same because each clients will have their own data set and they do stochastic gradient. So that their model update will definitely be different. But in this paper, the author treat the differences between local model updates across device as noise, so that then they focus on recover for each user the average model update. And so in this case, in some sense, the aggregated model update matrix is the P times the average local model updates plus some noise. So it reduces this constraint to minimization, so that it will not be so strict. And then this problem can be solved by like using the linear integer programming solver. Let's look at the experimental results of this paper. In the experiment, the author first observed the success rate of recovering P on synthetic data. So they generate some synthetic gradient, that is a synthetic local model update matrix and the synthetic aggregate matrix, and sum them together to get the synthetic sum of model update. So the goal here is to, given the synthetic model update, how to use their method to recover the P, and then they report the success rate of recovering P in this setting. Here, they evaluate the following metrics. The first one is the number of rounds, which is the total number of training rounds, and the number of users, which is the total number of users in this Federated setting. Here from this figure, we can see that as the number of rounds increases, the attacker can recover the matrix P with 100%. So however, as the number of users increases, it becomes harder to recover the matrix P. The reason is that more rounds of observed gradient can increase the construction success rate, and more users, which means this matrix P to be recovered is very large, and recovering the P becomes harder.
So here, why? So I thought the goal is to construct the individual gradient update, right? So
Yeah.
why do they want to show how to recover this user participation matrix here?
Oh, because for the server, if you recovered the P, and the server has the sum of the model update, and the P times the individual model update is equivalent to the sum of model update. So you can easily get the individual model update.
But if you load the user participation matrix, you load the sum. By solving that problem, there are infinite many solutions, a number of solutions about the individual update, right? So it's basically like you load the sum,
yeah.
but you don't know the individual, right? If you only tell me, well, this is A plus B plus C equal to something, I still don't know A plus B plus C. Do they have established the algorithm to infer A, B, C from the sum?
Yes, but they I can go back to. So the problem is P is unknown, and G individual model update is unknown for the server, right? Yeah. And the aggregation is known for the server. And Then to solve this problem, we first recover P individually. And as now we got the P, we can, the G individual is equivalent to P to the power of 1 minus 1 times G aggregate.
Not necessary. If P, for example, if P is not invertible, you cannot put there.
Yeah, but they said that they still can be solved by like linear programming, right?
Yeah, I guess here the main I think it makes sounds counterintuitive, but I guess the main idea here is like maybe in one round, knowing the participation and the sum is definitely not enough for you to infer individual gradient, but knowing multiple participation, multiple lines of P, it may be easier to infer the G, but that depends, do they have like underlying assumptions saying that the G does not change? Because if G changes, then it still cannot be solved, even if you have a large P.
Yeah, that's why they have an assumption that G does not change, because they have an assumption before, like about the capability of the server. It's like the server is the adversary and can fix the global model across round. I think the reason they make the assumption is like if they fix the global model across round, and then
got it. So it's like they are manipulating the global model so that they are enforcing each participant to perform the same gradient updates.
Yes.
So they only even the server send the client the same global model. The model update will be slightly different as well, right? Just because you have a stochastic gradient. So that's why.
Yes, I understand your problem. So because it will not be exactly the same, right? But they take this difference as like injected noise.
Yeah.
They first, so the problem will becomes to the sum of average model update across devices and some noise, right? Equivalent, which is equivalent to the aggregated modality. So their first step is to denoise. They use SVD to denoise the aggregated model update. And then their goal becomes to recover the average model updates for clients. This is kind of like
yeah, I understand. Yeah, I understand what they're doing now. Yeah, basically, but it's weird here. So why? You assume that you are server. What's your goal here? Your goal. So I mean, the first question is that why does the server care about individual model update?
Because if the server gets the individual model update, it can infer the local training data, right?
We don't, but yeah, that's true. That's true. However, if your final goal is just trying to get the training data of an individual user, you don't necessarily need to go to the immediate step saying that I want first need to get your individual mode update, and then from the individual mode update to get your individual data,
Okay.
right?
Yeah.
I can just start from the sum. The sum is, even for the sum, they can leak, under all kinds of assumptions that in the model inversion attack or membership inverse attack, they actually can get some information about the individual user data, right? So
yes,
I think you're talking about different attacks, right? That's like you based on the differential or something of the sum, you can infer certain kind of model updates from certain users. That's true, but I think that's a different attack.
Well, for this paper, they did mention like the membership inference attack or model inversion attack. They can be used on the aggregated model updates to infer the local training data, right? But as more and more users participate in the aggregation, it becomes harder and harder to infer the training data because everyone had it in the cloud.
Yeah.
So by using the disaggregation, the server will first obtain a approximated local model update and then do the inference, and the success rate will be higher in this case.
Well, I think that's not a fair adjustment. I think the only problem they have is they rely on different assumptions. That's the only thing, right? So you cannot say, you know, their paper, I mean, their approach is better than the differential attacks, this kind of inference attack. It's not, because they're based on different assumptions, right? So I don't know why they make this kind of a judgment. But I don't think it's a kind of fair arguments there.
Yes.
I feel that you know, I feel that the problem is somehow created artificially.
That's true. They just have some linear algebra tools, then they try to go for a very old paper based on their knowledge. Then they try to, I don't know, launch this specific attack.
Yeah. Because if you think about the problem, looks like they, you know, on one hand they try to, you know, kind of limit the problem into a very special case, and then they want to, you know, you say that they fix a global across round. The central server, you know, is already doing something malicious actually, and now they say, oh, I'm worried privacy. Remember, you know, usually when we talk about privacy, we assume that all the parties, they are kind of like artists but curious, right? That's the basic means that while you are not interfere with the normal federated learning process. But now, if you see the assumption one, first assumption, they are basically trying to interfere with the normal federated learning process. And then based on this assumption, I'm trying to investigate the privacy attack. Well, based on this assumption, you can even investigate the more strong security attack. Because your server is adversary. Your server is adversary, you can do much more than what they consider here.
That's true. For example, if I'm a malicious server, I can only request one update from one user, right? And I tell you, okay, actually this another global update around, everybody submit. So for individual client, you don't know the truth and you submit, then they can easily get your model updates instead of using this very complex approach and based on a lot of assumptions. Yeah, I agree with Dr. Guo, yes. Yeah, if the server is malicious, is not kind of semi-honest, there's a much severe attack they can launch.
Yeah, I think to me, I feel that maybe they just, as Dr. Pan said, they have some technical, they are very strong in, for example, some linear algebra. So they're trying to say, okay, I'm going to do some research in privacy for the learning. So let's do that, how to map it there, and then how to create some kind of assumption there. Well,
yeah, but I think this paper does have some value that it basically illustrates another attack, and it tells you like secure aggregation is not enough. And I see they also have the code posted on the GitHub. So like
I mean, I know what you mean here.
Yeah, and for the central for what you just said, I agree that the central server, if the central server is adversarial, then a lot of bad things can be done. You basically can like ask all the others don't send and ask this user to send, and then you actually I think like the trying to learn the P is not that
difficult, right?
interesting. Yeah.
It's so easier for you to know. Yeah, if you are malicious, it's actually very
if I tell you that you have this information, then learning the P is so natural. And I guess, but I do, and I think one thing that is interesting is like they mentioned, there is a side information that the server can know, that is a user participation frequency.
Okay.
Yeah, and also like for when you say like if the central server is adversarial, it basically asks the users to send to calculate the same gradient repeatedly so that they can recover the privacy. I think another possibility is like if they do something like more obvious, they can easily get caught. But for this kind of thing, they may not be that easily get caught. And it is possible that they may, for example, maybe in from round 100 to round 150, they perform this and they continue to do the normal update afterwards. It's still, maybe the learning can still be ongoing.
Yeah.
So it may be more stealthy.
But it opens many options if you make that assumption.
Yes, definitely.
There are too many things to think
this
about.
May not be, if you have this assumption, this may not be the most interesting problem to explore.
Yeah. Under this assumption, you have more important and more challenging problem to investigate. So,
but I think I want to echo Dr. Guo, but I'm not an expert. So for this kind of client participation frequency, this side channel information, so is that possible? We can say change our IP address and fake our DNS address every time, so that, for example, I'm one of the client, right? But every time I participate from the server side, it seems like I'm a different guy. Well, I just contribute to my gradient. Is that possible? But Jiahao, I want to ask you, is that possible?
I don't know.
Yeah, because Jiahao, you're an intern with this, right? Is that possible?
Oh, I don't know that part. That's not my intern scope.
Oh, okay.
I think that's related to the Dr. Pan's question. I think that's related to the system implementation here. So I don't know, for example, what are the parties? Let's say if you have a trusted secure aggregator, everyone just send their message to the secure aggregator sum them, then just send the sum to the central server. Then they already actually hide all the IP address, user ID, because the central server don't need to know the ID of users. Now, of course, they don't. I think they cannot do anything related to the, the client participation. But if the user directly communicate with the central server, then that may be an issue, because the central server need to know who sent the information to me, things like that. I'm not sure how the system works, so it's not that straightforward here.
Well, I think it's doable, right? So we find this kind of crime every time they try to, attack certain kind of server with a different IP address, with a very weird IP address. So you cannot trace it back.
Yeah. Of course,
Yeah, but anyway, I agree with both of you. It's too many strong assumptions. Probably downgrade the value of the paper.
Maybe because they are from Harvard, so they can get accepted.
That should be double blind, right? So that's ICML should be double blind. Anyway,
maybe it's double blind. But if they post it in your archive, then that may not be the case.
Wow.
Because still, double blind, they does not prevent you from submit to the archive.
We're recording. I'm not sure that's the things we should discuss or not.
Okay.
We're
let's
gonna post it,
continue.
or we're gonna post it online anyway. So I
Continue,
don't want to cause troubles. Okay, Joey, please move on. Sorry.
Okay. So then they evaluate the participants, the success rate of reconstruction P with respect to different participation rate. And the participation rate is the fraction of participants chosen to participate in per round. And here we can see that a higher participant round requires more round to reconstruct P. So that's obvious because it becomes harder to construct the model update each round. And also they study the granularity of the sampling window of clients' participation frequency. Here, this figure shows that as the granularity increase, which means as the sampling window becomes large, which means we sample in a less frequent way. The number of rounds to achieve successful recovering of matrix P becomes larger, which means the matrix P becomes harder. That is reasonable because as we sampling the user participant frequency less frequently, it becomes harder. Less information we will get at each round. And also they study about the noise we mentioned before, because they make assumption that the user, the clients will have the same local model updates plus some noise. So the noise comes from either stochastic gradient or like the different distribution of training data. So they do some experiments about the successful rate of recovering P with respect to different data sets, different batch size, different number of local epochs, and using the momentum or not, or using a large fraction of the overall data set or not. So generally, a larger moment or larger data sets makes the recovering of P harder because model is injected. And then they conduct some the traditional gradient inference attack, that is the model inversion attack we know before, on the individual model update they recovered from the sum of model update. So here we can see that if there has only one user, which means there has no disaggregation or has disaggregation because it's just one user. So this represents that the model gradient inference attack on one gradient, it can recover the image for computing that gradient a little bit. And as more users participate in the aggregation, it's become harder for the traditional gradient inference attack to recover the image for computing that gradient. But if we use the gradient disaggregation before to get the approximated individual model update, and then apply the gradient inference attack on that approximated individual model model update, we can recover the image for computing that model update significantly.
So here I have a quick question. What they want to show here? I mean, if you want to show the advantage of their disaggregation algorithm, you should use the same picture, right? Instead of use three
Yes.
different pictures. What's the comparison trying to show us here?
Yes,
I got very confused. Yeah.
I kind of agree with you.
Oh, wow. Okay. Thank you then.
So this is their conclusion. I don't want to repeat their words, but the most, I think what I can learn from this paper is like we should pay attention to the side channel information the server can know that if, for example, when we do differentially private federated learning, if the server knows the side channel information, if they have, in this case, if they have more opportunities or higher probabilities to attack the model, to violate the client's data privacy. So that is for this paper. Any questions?